Hello, this is Mrs. Johnson. This is MAT221. We are in section 4.1, which is the beginning of Unit 4, which talks about the applications to the derivative. So we're going to talk about, section 4.1 talks about a concept called related rates. So first we're going to do a quick review problem. Remember back when we were talking about differentials and we were talking about approximations in linear approximations back in the last unit. We did a problem where we considered a balloon or a circle. In this case, I'm considering a sphere of radius 10. If the radius is changing at 0.1 centimeters, a very small amount, remember this is considered a differential because remember a very small amount of something is considered a differential, how much does the volume change? And we said, well, okay, the volume of a sphere, we look up that formula up online or in a textbook, and we said the volume of a sphere is 4/3 pi r cubed. Let's take the derivative of this, the rate of change of this volume with respect to the radius. Now 4/3 is a number, pi is a number, so those would just be constants. So I just have two variables here. I have v and r. So if I take the derivative with respect to r of this expression, implicit differentiation gives me that dv dr is equal to 4/3 pi multiplied by the derivative of r cubed with respect to r. And those variables match, so implicitly we just take the derivative, which would be 3r squared. And you notice that the 3 and the 3 will cancel each other, the 3 in the numerator and 3 in the denominator. So we get dv dr is equal to 4 pi r squared. Now, if we think of dv as a very small change in the volume and dr as this very small change in the radius here, we can use differentials and say that dv equals 4 pi r squared dr. And by substitution in this particular problem, it gave us that the radius of the sphere was equal to 10 centimeters, and the very small change in the radius was 10 centimeters. So we could get that the very small change in the volume is approximately 40 pi centimeters cubed. This would be an approximation because when we talk about differentials, differentials are considered a very small change in and are considered approximation values. So this value we consider an approximation. Now, suppose now we change the problem a little bit and we say that now we know that the radius is changing at an instantaneous rate of 0.01 centimeters per second. Now notice the difference in the two problems. Here we just said the change in the radius was 0.1 centimeters, but we didn't know how long it took to make that change. It just said that some period of time went by and the radius changed by 0.1 centimeters. But if we change the problem now and say that we know that the radius is changing at an instantaneous rate of change. This is the derivative. This is a rate of change. This is a derivative, and you can see it in its units. While before in the last problem, our unit was not a rate of change. It was just a straight thing. This was just saying a given centimeters. And here I have centimeters per second. So you can see that this is actually a rate of change. It is change in position over change in time. And it's telling us that it's happening at the rate of 0.1 centimeters for every second that passes. So there's a difference here now, a big difference, where we're given a derivative. Now this might be possible, by the way, if a sphere is something like a soap bubble or a balloon that we're blowing up slowly. Now if we look at this problem that we started with before, we'll start with volume and say, okay, what's happening to the instantaneous rate of change of the volume? We're going to take the derivative just like we did here, but now we're going to take the derivative with respect to time because time is now brought into the problem here. We're talking about the instantaneous. At this instant in time, the radius is changing by 0.1 centimeters for every second that passes by at this particular point in time. So we're going to use implicit differentiation again here, but we're now going to take the derivative with respect to time. What we were given here was the rate of change in the radius with respect to time, not just before in the last problem, we were just given a very small change in the radius. But in this particular problem, we're given the change in the radius over time, which is a rate of change, which is a derivative, and it is with respect to time because the rate is within seconds. So when I take the derivative implicitly here with respect to time, the derivative of v with respect to t is equal to dv dt. The derivative of the right side of the equation, the 4/3 and the pi, are just numbers, so they get brought to the front. Now I take the derivative of r cubed with respect to t. But remember, implicitly, if those variables are not matching, we use the chain rule. So the 3 comes to the front, cancels out with this 3. We subtract 1 from the exponent and get r squared. And then we take the derivative of the inside function with respect to the variable, in this case, t. So we take the derivative of r with respect to t, which we don't know what that is either. So we simply write dr dt. This is our application of implicit differentiation here. We're taking the derivative now with respect to any variable we would like, and in this case, with respect to time. Solving this equation by substituting what they gave us at this particular instant in time, I didn't state it in the very beginning, but the sphere is still 10 centimeters to start. So I would say the radius is 10 centimeters to start, so we would substitute 10 in for the radius. And we were given that the rate of change at this instant right here was given to us. The instantaneous rate of change, which is the derivative of the radius with respect to time, can now be plugged in here for dr dt. So we can now find the derivative of the volume with respect to time. Substituting in, doing a little bit of algebra and math, we get the rate of change of the volume with respect to time in seconds is given by 40 pi centimeters cubed per second. So for every second at this point in time, the volume is growing by 40 pi centimeters cubed per second. This answer, because we have an instantaneous rate of change and not just a differential approximation, we actually have a derivative to start with, is considered an exact answer and not an approximation like we do with differential problems. Differentials are just a small change in r, or a small change in t, or a small change in x, and are considered approximations. Here, derivatives are considered exact and are the instantaneous rate of change of the object at a given point in time. Now, related rates can be quite a daunting subject when we first begin. It seems like, oh, these are so tough, these problems. But as you move forward, you'll actually hopefully like these problems. They're actually pretty fun to do, and they're very much application problems in that we'll be using real-world applications of our derivatives. So here's a case where we say, if I have a 1 liter or a 1,000 centimeters cubed, which are equivalent to each other, tank, and water is draining from this tank at the rate of 3 liters per second. How fast is the surface of the water dropping in the tank? Now, this is definitely something we would do in an engineering problem. We used related rates back when there was an explosion a few years ago in the Gulf of Mexico. Do you remember there was a oil rig out in the Gulf of Mexico that exploded, I think there was even a movie made with Mark Wahlberg, something like that, on this particular incident. And it took several weeks before they could bring divers down to actually cap the oil well. So that oil was spewing into the Gulf of Mexico. So what scientists and mathematicians did is they actually were measuring the speed at which the oil was escaping from the pipes into the Gulf of Mexico following the explosion. And then from that, they could mathematically gather how much oil was spewed out into the Gulf of Mexico. And using these techniques of related rates, we could say, how fast is the oil, the big oil slick growing and everything. And so we did a lot of mathematical work and engineering work during things like this. All right, so let's go back to this problem and say, how fast is the water dropping in the tank? Now, what are we given and how do I know this is a related rates problem? By the way, these problems are called related rates because we're relating two derivatives. Notice in the last problem, we were relating the volume derivative with the radius derivative. So the derivative of the volume was related to the derivative of the radius with respect to time. So notice we have two rates of change or two derivatives, and they were related to each other. So let's look at this problem again. Now, what do we know? We know that from the given information, the volume of the water in the tank is falling by 3 liters per second. So I know the instantaneous rate of change in the volume because it told me the water is draining from the tank at 3 liters per second. That means my volume of my water must be draining or decreasing, so I put a negative, by 3 liters for every second of time that passes at this particular instant. All right, what else do I know? I know that because every 1 liter equals 1,000 centimeters cubed, I could replace this using dimensional analysis with negative 3,000 centimeters cubed per second. Now we could leave it in liters also. Both are appropriate. All right, so what else do I know? I want to find how fast, or in other words, the rate of change in the surface of the water. And remember, the surface of the water, if we think of this as a tank, this is a circle here, the surface of the water. We want to know the height of the water, right, which is how fast the surface of the water is dropping down the tank. So we want to find what is the difference in the height of the water of the tank? What is the rate of change of the height of the water in the tank at any given time, t? So we need to somehow find a formula that will relate these two rates. We want to relate volume and height of the water. Well, the volume of a cylinder relates these two things. The volume of a cylinder, if we look it up in the back of our book, or we look it up on YouTube, or we look it up on Google, the volume of a cylinder is equal to pi r squared h. So we notice that the volume is related to the height of the water, but it's also related to the radius of the water. And that might be a problem. Or is it? Well, let's think. If we think of, in this particular case, a cylinder, the volume of a cylinder, does the radius change? Well, we know the volume is going to change, and we know the height of the water is going to change, but will the radius of the tank change, or the radius of the cylinder change? And we say to ourselves, well, no, it won't. With a cylinder, the radius of this tank is always going to stay the same. It's not going to change. So we can think of the radius as actually a constant. No matter what the radius is, it's some constant number. It's not going to change. However, the volume of the water in the tank will change, and the height of the water in the tank will change. So when things are changing, we have to keep variables in there and think of them as variables and changing. When something is not changing, like the radius, we can think of them as just a constant, and we'll treat it just as if it was some number. All right, that